Hello, my name is Maisie Anderson, and this is my lab report for Lab 3, Circuits for Physics 2212. So firstly, what is the purpose of this lab? The purpose is to predict how a circuit acts with different batteries, resistors, and capacitors in series and in parallel, and use multimeters to measure the current/potential of the circuit. The experimental model was the physical circuit in lab, in which the system was the circuit and the surroundings was everything else. And as a brief preview of the results, the 47 ohm resistor has a potential difference value of 0.92 volts. The 100 ohm resistor has a potential difference value of 1.96 volts. The current is 19.1 mA, and the charging time was 2 seconds, and the discharging time was 40.95 seconds. So the fundamental principles in this lab are the node rule, which states that the current going into a node has to be equal to the current flowing out of the node, and the loop rule, all electric potential differences around a loop must add up to 0, and Ohm's law, where V equals IR, so between 2 points, the current through a conductor must be directly proportional to the voltage between them. So here are just images of our in-lab circuits. So part 1 in the image up top had 2 batteries, 2 ammeters, and 2 resistors. And then part 2 had a capacitor, 2 batteries, and a light bulb. So for our results, we found that the current was equal to 19.1 mA, and if the ammeter connections were switched, both readings were negative but the same magnitude. And this was the case through both resistors, etc. When we changed the ammeter to a voltmeter, it had a reading of 3.1 volts, but then when we changed it to an ammeter, it had a reading of 0.3 mA. And this is likely because the voltmeter had a much greater resistance than the ammeter, so it decreased the current severely throughout, or as it changed. And then we found the sum of the potential differences across the circuit to be 1.71 volts, although the theoretical value should be 0 volts through the loop rule, so this could be due to errors that I'll discuss later. And I calculated the resistance in each of the resistors and the wires and the ammeter based on our measured voltage and our measured amps, and found that for both resistors, the resistance was calculated to be slightly higher than the given value for the resistor, which could be due to the wires having taken some of the charge and the charge being lower, or for other reasons. So in terms of analysis for part 1, the ammeter readings don't change due to low resistance in the ammeter, as the current is not affected as it flows through, but since the voltmeter has high resistance, it alters the current as it flows through. And then the resistance of each resistor was calculated to be higher than expected, as I mentioned before, which could be due to loss of charge to the wires or the environment. And as we see in this diagram, as the current flows through the entire circuit, the charge increases as it goes through the battery and then decreases back to almost 0 as it goes through the resistors and the ammeters and goes back to the starting point of the circuit. As for our part 2 results, we found that as the capacitor charged, the light bulb's brightness decreased, and as the capacitor discharged, the light bulb's brightness also decreased, because in both cases, as this is occurring, the current going through the actual light bulb keeps getting smaller and smaller, so the brightness decreases. We found the charging time of the capacitor to be 2 seconds and the discharging time to be 40.95 seconds. And it makes sense that the charging time is much faster than the discharging time because the charge has to go through much less to get into the capacitor, but as it's flowing back out, it goes through much more areas of resistance, so it takes a much longer time. So possible errors in this lab are that we had inaccurate measurements from the voltmeter or ammeter, our battery might not have been fully charged, and air could act as a conductor and may reduce the charge, and the capacitance of the capacitors might be inaccurate. So as for the discussion, what if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? The capacitor would charge much faster because the current would flow directly into the capacitor with no resistance in the circuit, likely occurring instantaneously, but this would not happen in real life because batteries and ammeters have some small degree of resistance, which slows the charging time. And then when we measured the amount of time that it takes to charge the capacitor, it took longer than the predicted instantaneous time. It took several seconds, which makes sense for the reasons I just discussed. Thank you.